Digestion, pyrolysis, gasification. I'm Eric Freyer from GRDF, the main gas DSO in France and in Europe. We'll discuss about links between biogas and biochar production, not only on the energy side. So for each speaker, it's the rule. You will have each 20 minutes, 15 minutes to talk, and 5 minutes to query and answer afterwards. So we have changed the order of the speeches, but it's okay for you. To introduce, I will like Melissa from GECA, GECA Environnement. You can introduce yourself, your company, and start the more general purpose.
Hi, everyone. I'm replacing Suzanne today. Suzanne, the CEO of GECA. She was supposed to give a talk, but unfortunately, she caught a bad flu and couldn't make it across. So I've, oh, I didn't know. I thought we were all introducing ourselves. Okay, sorry. So yeah, I'm replacing Suzanne today, and her presentation was about how can gasification and pyrolysis actually, benefit RNG processes, RNG plants. I have made it very short and sweet. I think it's going to be good for an introduction. Do you have a clicker? It's going to be good for an introduction. So we can set the stage for the two other presenters that are there. Thank you. All right. All right. So just providing context, and then kind of providing some elements, very few elements on how to use pyrolysis or gasification and or the products of them around, anaerobic digestion plants, so for biogas. So shout out to my team who last night built some tables and some slides so we can replace Suzanne briefly today. Brief overview, sewage sludge and digestate. We really took a look at it in terms of also involving biosolids here. So current usages, as most of you know, agriculture where it is land applied. In some jurisdictions, it's also landfilled. The sludge that come out of it, the digestate that come out of maybe less the digestate, but mostly the biosolids. In other jurisdictions, there's also incinerations, and it can be composted, of course. So those are the current usages of these materials coming out. In terms of regulations and certifications, I won't necessarily go through it, but there are some changing directives, there are some new regulations. We're also seeing that there are changes across the ocean as well, where we won't necessarily be able to land apply sewage sludge, biosolids, or even digestates, depending on the feedstocks, on agricultural land because of contaminants in some instances. And so there has to be other solutions, right, to this material, which is biogenic, still has, plenty of qualities and things to offer. So this is why we're talking today about pyrolysis and gasification. What is driving the opportunity with these materials? So again, manure, sludge, digestates after anaerobic digestion, and biosolids that come out of wastewater treatment plants. Project developers, technology manufacturers, and even some municipalities that are dealing with the materials themselves are looking at pyrolysis and gasification more to treat these. So the drivers for the adoption of these, I'd say, processes would be likely the regulations that we mentioned, right? The tipping fee increases, so when they're sending it into landfills, tipping fees are starting to skyrocket. There's not a lot of space in landfills, and there's a big, I would say, a blockage of new landfills opening, which is really limiting the spaces. And so there has to be ways to monetize rather than pay to get rid of. In the EU, there is also a push to recover more phosphorus and to depend less on imports of phosphorus from other jurisdictions. The other piece is when project developers think about pyrolysis or gasification, they're also viewing digestates and biosolids as a very low-cost feedstock. Whereas most pyrolysis and gasification is done with, wood waste, or even more and more agricultural waste, there is still a significant cost that's linked to either purchasing or generating these materials to the facility itself. So digestate, in some cases, and biosolids really provide this opportunity to optimize the economics of the project based on purely the cost of biochar. Now, of course, they make different products, but nonetheless, that's something that we see that is quite interesting. And even so more for biosolids, where these plants can receive tipping fees actually from taking this material. And the last piece is carbon removals. Obviously, you know, there's a lot of stand here on carbon today. We do carbon project development. Our clients, they get into this space also with the intention of generating carbon revenue, in addition to the tipping fees, in addition potentially to even also selling the biochar. So it becomes, you know, stackable, all these revenues. So this is a very similar table, just comparison, but for the biochar from sewage sludge. The current usage are varied. It depends if it is digestate or sewage sludge biochar. It depends on the properties of the biochar, but generally we see that it's used in agriculture, in construction materials, for composting, for example. So the standards that have to be respected for agriculture are very important. I think, you know, CSI just right at the back are handling the EBC and water biochar certification, which are just right here listed. And it also provides a really interesting value in terms of a tonnage, right, compared to the feedstock. Of course, there are transformation costs, right? The important piece is what's net in there for us, right? But this is all down to the economics of it. And I would say that another driver, I guess I forgot to mention it, again, that's a little bit last minute, but is contaminants. So PFAS in biosolids particularly, and you know, other types of organic contaminants that can come also from anaerobic digestate, not necessarily from food waste, but maybe, you know, other types of feedstock, can also cause problems. And the legislation is, you know, coming into place to limit the usage or even to limit these contaminants, the environment. So when we're transforming them with pyrolysis or gasification at certain temperatures, in certain conditions, we can degrade these contaminants, or, you know, a big part of these. So now that we talked about making pyrolysis and making biochar, how do we actually use it? What is this biochar useful in when it comes from wastewater, biosolids, or when it comes from digestate? There are different ways of adopting it and using it. I've also included in this list the usage of biochar that don't necessarily come from these feedstock, but that can be used in processes around anaerobic digestion, for example. We've seen that some tests are being run for usage of biochar directly in AD reactors. Some results have come out with increasing methane yield, so that's pretty interesting, right? Increasing revenues from biogas. And we've also seen people using biochar in composting. So, for example, anaerobic digestion biochar can be used in composting, probably to accelerate as well the rate of the speed of composting. We also have a client that has tried putting biochar in manure lagoons for treatment, and when they showed up 2 days later, there was barely any smell in pig lagoons. So that's pretty wonderful, and it's really around, again, you know, this anaerobic digestion and methanization processes. Finally, 2 examples, and I'm sure that, you know, maybe some people will talk a little bit about these too, but there also have been some trials more and more for H2S sorption or removal, I would say, in the treatment of the gas coming out of biogas, and also in animal bedding. So this is where that's a really good example of biochar from anaerobic digestion can be put in animal bedding, chicken litter, for example, to absorb ammonia, reduce, you know, pulmonary diseases, and will reduce odors, of course. So this was very brief. Really quickly, what we do at GECA, we have a booth. It's J39, I think. It's right over there. And we do a lot of project development acceleration where we help project developers build robust projects that withstand stress as much on a technical level and as possible on a financial level as well, where we do also de-risking. So processes, technologies, making sure that we're integrating as well physical products with the carbon products, so that everything is optimized. We do a lot of strategy as well, helping build pipelines of projects and making sure that we follow, understand, and comply with upcoming regulations that are changing very quickly. And the last piece of what we do is we're in the ecosystem, advocating. We're trying to educate a lot, and we make sure that we follow also the development. So looking into the new technologies, the new usages. So we're having a researcher here that's probably going to talk about some exciting things, I think. And so this is the type of thing that we want to follow so that we can bring them into, businesses, into new projects. So that's all from me. I hope it addressed a very basic layer so that we can get into more depth with the two next panelists. Thanks.
Thank you, Melissa. Maybe it's time for some questions for specific question for Melissa from the floor. No, no more question. It was clear. So next one, maybe Jesper AHRENFELDT, coming from Denmark and from Stiesdal. We'll talk about this very specific process and project in Denmark about pyrolysis. It's up to you.
Thank you very much. Yeah, so my name is Jesper AHRENFELDT. I'm a chief engineer at Stiesdal SkyClean. And what I want to present today is an overlook of our first full-scale plant that we are commissioning as we speak. So it's a 20 megawatt pyrolysis plant, which is integrated with a biogas plant. So it's going to produce biochar on the digestate, so what we call biogas residue fibers. And we are going to produce heat for the biogas upgrading in the biogas plant. Just briefly where I come from. The main company is called Stiesdal, and we have 4 subsidiaries working with different kinds of technologies for climate solutions. So we work with offshore floating windmill foundation, we work with energy storage, we work with electrolysis, and then we work with carbon removal, which is through pyrolysis. The basic idea of producing biochar is kind of laid out in this nice little cartoon. So we let nature do the job of taking the CO2 out of the atmosphere. We take residues primarily from agriculture. We also work with forest residues, but primarily with agricultural residue. We take the residues and then we do pyrolysis. We make biochar with a high permanence, and then we use the gaseous products for energy purposes. And with the one I will talk about today, it's the simplest way of utilizing the gas, so it's just pure combustion. So the way we do pyrolysis is that we have what we call an updraft pyrolysis reactor, and for that to be as smooth as possible, we use pelletized feedstock. So we have our own pelletizing. We also have drying if it's a wet feedstock, which digestive usually is. The nice thing about doing pellets is that you have a very smooth operation of the process, but also in this process you get the biochar out as pellets afterwards. So when you look at the whole value chain, you will need to bring the biochar back to agriculture. We are focusing on very big plants, so we are going to handle a lot of biomass, and we are going to handle a lot of biochar, and primarily in an agricultural context. So we need to have something afterwards that is durable to handle and durable to spread out, but I'll get back to that. We are not an old company. Basically, we started with pyrolysis a bit more than 3 years ago. The process that we have came from the Technical University of Denmark, and that's actually my background. I worked there for 20 years with pyrolysis and gasification, developing new technologies. So I kind of took my baby under the arm and then went into this company. And then it's been a relatively fast track since then. So what we did was actually build a very small scale plant to begin with, but fully automated to get hold of the controls of the process. Then we built in 22 a 10 times bigger plant, which is still running, and it's in operation today as we speak. That is mainly fueled with straw pellets, which we buy commercially. Sorry. So all the learnings we had from that, we put into the next scale up, which is our 20 megawatt plant, which we have built right now, and it's being put into operation as we speak. It's, as you can see on the picture, it's placed next to a very big biogas plant. So it's, I think it's producing around 15 million cubics of upgraded methane a year, so it's quite big. And where we are right now, where we built this pyrolysis unit, we call it a 20 megawatt, but right now there's not feedstock enough for more than maybe 12 megawatt input, but it's built for 20 megawatt because they are going to build out the biogas plant quite soon, so it's more or less going to be doubled. So we are starting the commissioning right now. It's rather complex because it's integrated with the biogas plant, but again, as Melissa pointed out, it's on the other hand a cheap feedstock for the pyrolysis. We will produce around 7 megawatt of energy when we are up in full scale. There are a surplus of energy, which is cooled away right now, but that's only because the plant is not connected to the district heating grid, which we have a lot of in Denmark, but is prepared for that. We need to do some piping for the nearest city because, of course, this is placed outside of settlements because it's a very, very big biogas plant. So the basic idea is to produce carbon capture via biochar, which corresponds to around 28,000 tons of CO2 equivalent a year. On a sketch, it looks like this. So we have what we call the wet building, where the digester is dewatered. Then it goes into the SkyClean building, where there's a disc dryer for drying the feedstock. Then there's a pelletizer. There's a pyrolysis unit here. The gas goes outside into a separate boiler room where it's combusted. And the hot exhaust gas is used for running, of course, the pyrolysis, but also running the dryer. Out of the dryer comes pressurized steam at about 4 bars, which means that we can condensate that steam out at around 140 degrees, which is temperature enough for the upgrading of the biogas. So that heat goes to the amine plant at the biogas plant. In real life, it looks like this. So this is what we call the wet building. There we have the SkyClean building, and then we have the boiler room. Over here is the existing amine plant for the upgrading of the biogas, where we're going to deliver the heat for that. So today they burn methane to heat up the amine plant. So there was actually going to be an increase in the net production of biogas from this plant, because they're going to we are going to deliver the heat for the plant, so they don't have to burn any gas. Yeah, so So with this, we will have CCS production with the biochar. We will produce energy for the biogas plant. Yeah, we will increase the net production of the biogas plant and of course the CO2 footprint. We are selling, as to begin with at least, we are going to sell carbon certificate. We actually managed to sell the first ones from our smaller plants on straw, so we are getting the first experience with selling carbon certificates from biochar. So in the future, the idea is that these plants, energy islands or energy parks or whatever you want to call it, that they are self-reliant with energy, both heat and electricity. So in an overview, it looks like this, where we have the biogas plant, we have dry matter to the pyrolysis, we do the carbon sequestration, and we return that to agriculture. We sell some carbon credits. We could also in the future sell district heating, and then we have this heat integration with the biogas upgrading. For the carbon credits, it looks like this. So we have the dry matter going to the pyrolysis, then we have the biochar. Because it's digestive, there's a lot of ash in the biochar. So more or less half of it is ash. But there's also carbon, which is equivalent to these 28,000 tons of CO2 a year. But then there will be an additional displacement because we handle the wet feedstock, and also because we are not consuming biogas for upgrading the biogas. So overall, it looks like this. And the biochar, the ash, that has some fertilizer value. To begin with, we are not going to try to sell that fertilizer value. We are giving it away to the farmers who will take the biochar. So they will get kind of a small benefit of getting the biochar and incorporating that in the soil. But we don't put any value on that at the moment. The economics of this looks like this, at least in Denmark. So I apologize, this should be CO2. So we will sell some CO2 certificates. There is going to be most likely some subsidies in Denmark, at least for CCS. So we incorporate that, we will sell some energy. And then there are these savings for the biogas plants. And then, of course, there's some OPEX, and it will cost a little bit of money to, of course, distribute these relatively large amounts of biochar. But one of the things we are looking into is, instead of selling carbon credits, is seeing the biochar as giving value to this thing called the carbon intensity score for the biogas. So instead of going out and selling carbon credits for the biochar, you could incorporate it in this carbon intensity score for the biogas instead. So we, together with consultant companies, we are looking into this. If this is doable, if it is, it's a relatively easy way to handle the biochar, but it also gives a lot of value to the biogas. So instead of having a CI score of -20, we potentially can get to a CI score of -105. And that puts a lot of value for the biogas, or the biomethane that we produce for the grid. So basically what we are working with in this project, or in this scale-up, is the full value chain. So we have a lot of farmers involved in delivering feedstock for the biogas plant. These farmers are also involved in taking the biochar. And in between there's, oh sorry for that, back. There's the technology, so the biogas technology and the pyrolysis technology. And then of course there's some, there's the whole economic basis of the plant. But from the beginning on, we involved the farmers a lot, both on down to the single farmers, but also the farmers' organizations, and also cooperatives of farmers, and they are also going to invest in these plants in the future. Just as an example of that, we do a lot of soil trials with our Biochar, and we are going to do that for many years in continuous trials. But on one of the major things to begin with was, are we able to handle the Biochar in our agricultural system? Are we able to use it in existing equipment? So this is an example of that. So because we have the Biochar as pellets after the pyrolysis, it's relatively easy to use it in existing farming equipment, and we tried several solutions for this, and it's fairly durable to do that. We wet the Biochar a little bit when we get it out, primarily to avoid self-ignition, but also that it doesn't create dust and it's easy to handle, and that is actually looking to be quite straightforward. The important part when you want to use the Biochar, of course, on agricultural soils, is that it's a clean Biochar. The permanence is of course important, so we do pyrolysis at 600 degrees, so we have an HC ratio of about 0.3, but we also of course want a clean Biochar, and we put a lot of effort in controlling that from the very beginning. Luckily, I had experience with that from the universities, from my previous life. But we can comply with all the standards in our process. And for the Biochar that we have made on straw, we already have a EBC certificate, and we have, of course, made measurements also on the Biochar made from the digesters, and we are going to get a EBC certificate on the new plant as soon as it is in operation. We have this on our webpage if you want to go in and have a look. I would also like to refer to our webpage because we had a press release yesterday that we are going into a joint venture with a big biogas plant producer to build very big plants, and we are talking about 60 megawatt of pyrolysis together with biogas plants. So if you're interested in that, have a look at our webpage or come to our stand over there at G28. That was it.
Any questions for Jesper?
Hi. Have you had any trials or experience of mixing the digestate raw with the biochar from the digestate?
No, not exactly that. No, but we have had talks about that also, especially with our university partners. We are also looking into actually mixing feedstocks before we pelletize, because if you work with pelletization, you know that straw pelletization is not very easy. Digestive is very easy to pelletize. So in the future we might look into mixing different feedstocks, but that's only been done at very small scale. But we not looked into recycling but there's been talks about that, yes.
Hi. You mentioned about subsidy for the farmers. In what form were they having subsidies in Denmark?
No, the farmers will not have subsidies. There'll be a CCS subsidy for carbon sequestration through biochar. As it is now in Denmark, the farmers, they want to take the biochar because they're pressed. The carbon footprint is not very excellent in farming, so this is a way of, on a national level, to bring down the carbon footprint of farming. So that's why they are relatively eager to do this. And then, of course, if it's biochar based on digestive, they get nutrients for free. But what we are looking into is very much incorporating the farmers as co-owners of these plants. There's a strong tradition in Denmark for the farmers to go together, building dairy companies, building slaughter companies. So they also want to do that with biogas and pyrolysis.
You mentioned the carbon intensity.
Yeah.
The biogas increases, when you add biochar.
Yeah.
Does that mean then when you've looked at the financial model, the income is also better rather than carbon credits? And if it is, how much more would you be getting by doing it that route?
Today it's better, at least. I mean, in the calculation I had, we based that on a carbon credit price of around 100 euros per ton of CO2 equivalent, and I cannot tell you the numbers if we add it to this CI score instead, but it's definitely better. But of course, you don't know where the carbon credit market will move. Perhaps it's going to be a better business to sell carbon credits than incorporated in the CI score. But today it will definitely be a better business to do that.
Thank you.
Just one question, Jesper. You said you plan to use the biochar as a fertilizer, but I think it's not alone. You have to activate maybe with digestate. Yeah.
No, I mean the phosphorus and the potassium is quite plant available. It's not a starter fertilizer, but besides that, it's very plant available. We done several tests with that. Of course, you need to add some nitrogen. Yeah, but in Denmark we have this. There's a limit to how much phosphorus you are allowed to spread on farmland. And for some reason, many of the biogas plants are placed in the same area. So there's a surplus of phosphorus. You need to redistribute that to another part of the country. And if you have it as a wet digestive, it's too expensive to do that. But if you have it as a dry concentrated biochar, then it's much easier. So that is another advantage. So then you have most of the nitrogen you will have in the water when you dewater the digested. So all the nitrogen goes with the water, or most of it. All the plant available nitrogen goes with the water. The small part that's in the fibers, they will go away. So they will go with the gas in the pyrolysis plant.
I have a question about how much phosphorus do you have in the char after digestion? I mean, produced from digested.
That is very dependent on the feedstock, on the biogas plant, because in this plant, one of the main features here is that they can handle a lot of straw in the biogas plant. So there's relatively more straw than you usually have in a biogas plant. So there's not significant amount of phosphorus. Other biogas plants, you will have a much higher phosphorus in the biochar. So it's very dependent on the feedstock.
Yeah. Okay, it's my turn then. Okay, how it works?
So it will be a different use case depending on different feedstock.
Much different. Waiting for the slides. Yeah, that's it. Okay, and okay. Okay, well, hello everybody. My name is Andrea SALIMBENI. I'm head of unit at Record. Record is a private research center based in the province of Florence. The study I'm presenting with this long title is about the integration of anaerobic digestion and slow pyrolysis applied to the organic fraction of municipal solid waste. So I said, much different substrate to treat. Briefly, the case study, it's a plant to be built still in the province of Florence with a capacity of about 40,000 tons per year of bio-waste. Bio-waste means, in this case, organic fraction of municipal solid waste, and 2,000 tons per year of green waste, prunings and residues from urban green areas maintenance. Production of biomethane is estimated about 2,200 tons of biomethane per year. CO2 is separated from the biogas and liquefied. The production is about 3,700 tons per year. And then production of biochar in the range of 1,700 tons and ammonium sulfate at 33% concentration of about 2,400 tons per year production. These amounts are those that have been presented as a project to have been the authorization of the regional authority in Tuscany. As you can understand from the list of products, the plant will consist in an integrated plant for biomethane and CO2 liquid production from anaerobic digestion, and biochar production from the pyrolysis of the digested solid fraction. The liquid fraction that we obtain after the separation of liquid and solid phase is treated by ammonium stripping and sulfuric acid for precipitation to produce ammonium sulfate. Well, some information about the energy balance are reported here, even if, of course, we have not yet a plant ongoing. So what you see here is the result of a calculative study to integrate the energy of the process. Of course, we recover energy from the pyrolysis. Pyrogas is about 900 kilowatt of chemical energy recovered by thermal oxidizing the pyrogases. An additional amount of natural gas is used, because here we are not talking about an energy plant. We are talking about a materials recovery plant. So our target is to be more than self-sufficient. Of course, we produce about 4 megawatt equivalent of biomethane. We consume about 2.4, estimating. We can consume less, but this is, as said, it's a study where we use the thermal energy. We use thermal energy to dry the solid fraction after centrifugation. We use thermal energy for the stripping unit, because for stripping ammonia, we need to heat up the liquid phase at about 60, 70 degrees. And of course, to provide the thermal energy for the anaerobic digester, which is a thermophilic digester. So it works at 55 degrees. So this is how we use the energy, and our target, as said, was to be self-sufficient, more than self-sufficient, and to recover products from the waste. So the process concept and the carbon balance is briefly reported. Here you can find an average carbon distribution between the products. We have about 1,000 in the organic fraction of municipal solid waste. We get about 270 in the digested. So our target was to make the 270 tons of carbon as available in terms of products. So usually after centrifugation, there is a carbon lost in the liquid phase. We must take in account that. And then we go to stripping. We do not recover actually the carbon from that. We recover the ammonium sulfate. Then the solid phase with the rest of carbon usually goes as a digested, could be already a component material according to the fertilizers regulation. It can be a product fertilizer category 3 as a soil conditioner, but it can also mix with green waste to produce compost. That is the traditional system. Compost is, as well as for the digested itself, a component material, and also can be a product function category according to our regulation. But that is what we do. We do drying, and then we do pyrolysis. The water that we remove after drying goes to the stripping unit, and then the pyrolysis enables to recover biochar for about 195 tons of carbon and about 175 as a pyrogas, because of course we lose part of the carbon in the gas phase. And that amount of carbon is that the carbon that we consider not recovered as a material. The biochar is a component material, CMC14, and it can be, we will see later on, a product itself, like compost. The difference here between the composting process is that we immediately lose part of the carbon by devolatilizing with slow pyrolysis, but we fix 18% of the initial carbon as a char, and that is eternally fixed. So that is the target, storing the carbon. So the concept is supported by what Jesper was saying about the value of the product. Of course, if there was ash in the digestate after agricultural waste digestion, there is even more ash in the char after the digestion of organic fraction of municipal solid waste. But we can reasonably consider that we have 1.5, 2.5 ton of CO2 saved in 1 ton of char because of the equivalence with the molar mass. In this case, we can say that we store part of the carbon, 18% we saw before in the slide before, 18% of that carbon is stored in a long-lived carbon source. Where the value of the biochar stays, we have to be also clear. The biochar and the agricultural is not in the European trading scheme. So there is not a CO2 price of 100 or 85 euro per ton now. So we cannot claim immediately that that char gets that amount and that price because of the CO2 stored yet. Because there is no one that can claim to the European Commission that that CO2 was absorbed within the ETS. Not yet. At the same time, there is no doubt that that CO2 is absorbed. The value, it's something that depends on the market. Voluntary credits ensure a value of the product, and then depends on the market. You can get a certification, but then it is really on the market, and different estimations can be done about the price. 100 euro per ton of CO2, 200 or 20. Depends on where we are and how the market is going. But at the same time, we can trust on the fact that carbon farming and the application of an emission trading system to the agricultural sector will be soon under discussion. So we have to consider that we have a baseline value, which is the market value of the product, which is 100 euro per ton. Reasonably, without any price of CO2, that product is already a high-value product. So count on that as a valuable product to be used in agriculture. Then any additional value which we can obtain thanks to the new ETS or to any carbon credit, it's an additional point. But what we have to trust on is the contribution of this product to sustainable agriculture. Briefly about the normative context, as I said before, we have a conventional solution which brings to the production of CMC5 solid digestate because of a thermophilic anaerobic digestion, because our regulation says that the digestate solid fraction is a CMC if the anaerobic digestion was done at thermophilic condition, because it's stabilized. And that is a bio-waste treatment plant. Then the second part is including the addition of biomass as an additive and the production of a char, which is actually a fertilizers production plant, because we are mixing two products to produce another product, which is again a product under the regulation, as Jesper described before. Of course, we have to comply with the limits, because if we do not comply, that is an issue. So the first aspect to take in account to be sure that all these business models stay and it makes sense is that the inlet material, the organic fraction of municipal solid waste, in this case, complies with the quality that we expect to have at the end. So taking account the heavy metals concentration is the first thing that we have to do. Otherwise, we risk that we build everything on a very weak structure. Going to conclude, what we wanted to do by this project is to realize a carbon negative plant, turning the organic fraction of municipal solid waste in 4 products and having thermal energy as an instrument to get these products. And in particular, to have a product at the end with relevant quality for the market, which is a biochar, with a higher market value than compost, and with even better market perspectives, thanks to this specific quality of absorbing CO2. Thanks so much.
Thank you, Andrea. It's a quite complementary approaches. Biofertilizer plant, and on the other side, it's to enhance the profitability of energy production using carbon credits. It's really interesting. Some more questions to Andrea?
Hi. How did you determine how much green waste to mix with the digestate, and did you try operating without mixing any, so doing the pyrolysis purely on the digestate?
Record is a research center doing demonstration tests. We have pyrolysis plants of up to 100 kilogram hour capacity, and we did a test with 2 tons of digestate. So we did, and we derived also the quality of the char and the mass balance that we can obtain by these tests. We did first 2 tests with a mixture of green waste and dry digestate in a 2 kg/h slow pyrolysis unit, condensing the fraction of the pyrogases and analyzing all the fractions to get quite a complete energy and mass balance. And then we did a test on a 100 kg/h unit to get also the evidence of the industrial feasibility of the process. It's done, I think. Okay. Can I sit?
No, of course. So maybe some points you want to tell with as a conclusion each.
I have a question for you, actually. I'm wondering the piece on pyrolysis and the treatment of basically the digestate. On the revenue part, what kind of revenue is it on the overall plant?
Well, the first source of revenue for this type of plants is the waste treatment fee, because treating the organic fraction of municipal solid waste is, I mean, it's a business that is based on a tipping fee that vary from 50 to 100 euro per ton of organic waste. That is why the traditional composting plants, they could sell the compost at 5 euro per ton so far, because the business and the payback time is driven by the tipping fee. In this case, the business model is a bit different because you have many products, so that you can count on for the sale of this product on the business model.
Thank you.
So it seems to be clear. We have to thank all the speakers, and thank you for listening and asking questions. Don't hesitate to see them. And it's a stand
G39.
Yeah.
G28.